All right, hello everyone. Welcome to Astronomy on Tap for May. This is a bit weird. We're all talking to our screens and all right, hello everyone. Welcome to Astronomy on Tap. Hold on. For all right, sorry about that. Did not mute my YouTube. So hopefully this is back to normal and everybody can see everything just fine. So this is Astronomy on Tap. This is our May version of Astronomy on Tap. So tonight we are going to have Dr. Jan Scholtz and Professor Kirsten Knudsen telling us about the massive black holes in the universe and searching for the earliest galaxies. So if you've been to our live locations here in Gothenburg at Hackett, you'll know that we have our two talks, and normally we have the quiz in between the talks. We're going to switch up the routine a little bit tonight like we did last month. So we'll have the two talks and then, oh no. Okay, and then we will have the quiz. Give me just a second. So I'm not sure what everybody, okay, cool. So Astronomy on Tap is a global coordination. It brings astronomy to the public. That's its main aim, and trying to get just more people involved in astronomy in general. It started in 2013, and it now has 40 locations across the world. If you're interested in learning anything else about it, then you can go to astronomyontap.org. So just a brief overview of the people who are here with you tonight. We have Andrea and myself as the host. Lewis is the question moderator, so he's going to be figuring out what questions people have asked in the chat that should be asked to the speakers. And then we have Iskra and Holly who will be doing the quiz. And of course, we have our presenters, Kirsten and Jan. So if you want to just say hi in the chat, just tell us where you're from, that'd be great. We have a bunch of other members of our team who are helping along the way, but are not on Zoom with us tonight. And if you are interested in connecting with us, you can find us on Facebook or on Twitter, or you can contact us with our email. Most of you have probably already found us through some sort of online way through Facebook or so on to find us here. Also, obviously, we have our YouTube channel, which is what you are watching right now. As I said earlier, the plan for tonight is to have Jan give a talk first about the most massive black holes in the universe, and then we'll take a short 5-minute break, and then we'll have Kirsten give another talk. So yeah, just keep on with us. And we should have, oh, if my screen decides to work. All right, if Jan is ready to share your screen.
Yes, I am. Should be. 2 seconds. Okay. So today, should I start or?
Yep. You are good.
Today, I would like to talk to you about the hidden monsters of the universe, the most massive black holes that are in the universe. And disclaimer, there are just not that many things that we know them. There are plenty of things that we are still trying to figure out. So sometimes I will not fully answer the questions because I will be like, I think we think it works that way. So first of all, it puts things into perspective. We would consider that, for example, Earth is something that is quite massive, right? It's a whole planet. Well, that one has something of an order of 10 to the 24 kilograms. So it's a pretty massive thing, right? It's a rocky planet. However, if you compare it to Sun, for example, Sun has a mass of 10 to the 32 kilograms. So it is basically 100 million times heavier than Earth. And sometimes because Sun is the most boring average star, it was quite a good unit of mass at the beginning. So we set up that there is a unit of mass called solar mass, and it's basically weight of our Sun. When we look further into the universe, we want to look at the most massive star that has ever been observed. It's a Wolf-Rayet star. Wolf-Rayet refers to the type of a star. And that one has a mass of roughly 320 solar masses, right? So again, it's 300 times more massive than our Sun. The thing is that stars are actually not that massive or that big. Galaxies contain millions and millions of stars, up to hundreds of billions of stars. So you can have a dwarf galaxy, which are basically just tiny little galaxies that are orbiting the proper big galaxies. And they have mass of roughly a million times the mass of the Sun. So they are quite massive. And then you have proper big galaxies. And those have a mass of anywhere between 100 million solar masses to 100 billion solar masses, or masses of the Sun, right? So where does supermassive black holes actually correspond to that one? Well, they are kind of in the middle. They are anywhere between 1 million to billion masses of Sun. Actually, they weigh 1%, up to 1% of the galaxy mass. So they reside in the center of galaxies, and they contain 1% of their mass. It's a brilliant thing. So what are black holes? Let's like backpedal a little bit. They are large amount of matter that's concentrated, so dense, it's in such a small region that not even light or objects that are actually traveling at speed of light can escape it and escape its gravity. So if you would have a black hole of one solar mass, it would be around 20 kilometers big, right? So you have an entire Sun just concentrated in a tiny, tiny region. When you look at these things that have 1%, the supermassive black holes that have weight of roughly 1% of a galaxy, they are concentrated in a region of a solar system. Right, so 1% of a galaxy mass is concentrated in a solar system. There's one thing: black holes are very common. We have these like regular sized black holes. They are just in every galaxy. There are hundreds and thousands of them. When it comes to these supermassive, these hidden monsters, every galaxy has one in the middle. They are very common. There is nothing special about them. By the way, a Milky Way, our own galaxy, has one as well. Pretty tiny one, only a million times the mass of the Sun, but we have one. How do you make a black hole? So when it comes to these ordinary black holes, which we refer to as the stellar mass black holes, that's ones we know quite well. You basically have a massive star that is dying. It ran out of fuel, and it goes supernova. And during a supernova, the core, the center of the star, of this massive star, can just basically get compressed by the explosion until it forms a neutron star. Sometimes it's even so big that it actually compresses the whole core into a black hole. When it comes to supermassive black holes, I'm afraid we don't really know. This is the first time I'm going to say we don't know, because we observed the first supermassive black holes that have mass of hundreds of billions times the mass of the Sun, roughly from universe of 10 billion or even more, even 11, 12 billion years ago. For any astronomers, is roughly the redshift to 6 to 7, where we see first of these massive masses. So they had to somehow grow in about a span of 700 million years since the Big Bang to these massive, massive things. And when you do a bit of physics, you realize that you can't grow them from a black hole that has 8 solar masses. It has to be way bigger. It has to be roughly 500 solar mass. And we call these 500 solar mass black holes as the seeds. And then they accrete, they basically absorb all that gas and material from around, and they grow into this massive thing. However, how do you create that seed? We are not really sure. There are some theories that they can be a number of small black holes that merge together. However, we don't really know how there would be so many small black holes so close together. The second option is that it's like a massive, massive cloud that basically starts collapsing. But again, we are not really 100% sure how you can make a cloud, just a cloud of gas, just start collapsing into a massive black hole. The physics gets really, really hard. So I guess your question when I talk to you about, when I explain what is a black hole is, if light can't escape black holes, how can we see black holes, right? That doesn't make sense. And you can never see a black hole as such, right? They don't emit any light. But you can see the gas, the material that is surrounding the black hole and that is falling into the black hole. And it's actually quite common for black holes to feed. They basically just, all that gas that's around them gets trapped in their gravity and they slowly spiral in. As they are spiraling in, they are basically going down a gravitational well. If you go down a gravitational well, you speed up. And in this case, they also the gas heats up. So you end up with this disk of hot gas surrounding the supermassive black hole, or any black hole for that matter. We call that disk, by the way, accretion disk, because it's accreting material. Accretion disks are, again, something that we actually study across all parts of astronomy. You can have an accretion disk onto a protostar that will eventually ignite into a normal star. You can have an accretion disk around a planet. You can have tons of different accretion disks. But these ones are special because we are talking about accretion disk around a supermassive black hole. So you see a galaxy in the top right, and in the middle of the galaxy, there is the supermassive black hole. When supermassive black hole starts accreting or absorbing all that gas, it becomes an active galactic nuclei, also known as AGN. You might kind of catch me using AGN or supermassive black hole. Just consider them their equivalent terms. Just AGN is an active supermassive black hole. And what you see when you have a active supermassive black hole, or AGN, is that, first of all, you can see kind of a donut around it. And this donut is actually dust. And this dust has a temperature of 200 to 800 Kelvin, which means minus 80 to roughly 720 degrees Celsius. And I will show you how we can see it later. Then you can see this accretion disk in the this accretion disk in the middle. That's gas that's actually falling in that has a temperature of roughly 5 to 30,000 degrees Kelvin. And then you might see like blue clouds. Unfortunately, my cursor is not working, but you might see like a blue cloud around the supermassive black hole. It's called the broadline region. And these are these small hydrogen clouds orbiting at roughly 7 or like roughly 5 to up to around 9,000 kilometers per second. They are really close and they have to orbit really fast in order to not to fall in. Also, if you look at the bottom right, you have another sort of zoom in onto the whole structure, and you can see that there's a sort of singularity, which we might sometimes refer to as the supermassive black hole, with sort of the event horizon, which refers to basically the boundary of the supermassive black hole. You see this corona of gas. It's a diffused, very hot gas that's sort of orbiting around it. So you might be wondering, how do we actually know so much about the structure around supermassive black hole? And that's because we can study them across different wavelengths with different colors of light. So on the right, you see what sometimes we as astronomers refer to as spectral energy distribution. And the spectral energy distribution is basically saying how bright is something at different frequencies or wavelengths or different types of light. So for example, the reason why we see, why we know that the dusty torus has temperature of roughly 200 to 800 Kelvin is because on the right, you can see sort of the red curve that's shining around near infrared and mid infrared, right? Around the 3 to 300 micron, as you can see on the top, on the top plot. And this basically refers to something that would emit light at 2 to 800 Kelvin. You can see the blue curve, right? That's something that's very much in the optical and the UV wavelength. And that one we know is comes from the accretion disk, and we know that it has temperature of roughly 20 to 50,000 Kelvin because it behaves like something. It actually behaves a little bit like a star. Stars can have temperatures around 5 to 50,000 Kelvin, and we can see it actually in the SED as the blue curve. We can see, for example, you can see also the jet, which is on the image on the left as the orange stream of particles. We see that as the orange thing on the SED is the radio wavelength that we see. So you can actually, by using all the different types of light, you can learn a lot about the structure of the supermassive black hole and the AGN. Now, one thing is, okay, have you ever seen one directly, or have you always kind of looked at the material that's surrounding it? And until last year, I would tell you that no, but in April 2019, Event Horizon Telescope published the first image of a supermassive black hole. You can see it on the top right. And you can see sort of like a donut of material. That's not the torus donut. That's probably some hot diffuse gas, probably the corona gas around it. We are not really sure. With a big black hole in the middle, and the big black hole in the middle is the supermassive black hole. This was done in the galaxy M87. And the way that astronomers were able to accomplish this amazing observation is that they linked radio telescopes from basically Hawaii to Europe to South Pole, and they connected them using this interferometry technique. If you remember Carmen's talk from the last time, you know all about interferometry. If this is your first time with first time you actually came across interferometry. Interferometry is this amazing technique that uses amazing engineering maths and black magic in order to link telescopes, radio telescopes, to act as a single telescope that's the size of the Earth. You can also do it using optical telescope, but that's super hard, and they can only do it in 2 or 3 places in the world, I think. Okay, so here we are going to have a question. I talked about how powerful supermassive black holes can be. I've shown how they can shine across different wavelengths. So now we have to ask ourselves, if supermassive black holes are really that powerful, if they can sometimes, some of the supermassive black holes can outshine an entire galaxy, right? They can be brighter than the galaxy, this tiny little thing in the middle, and can be brighter than billions of stars. Then can they actually change their host galaxy? Can they have impact on their host galaxies? Now, I have a big disclaimer here, because if you ask these questions at an astronomy conference, yeah, people are not going to agree. There are going to be I wouldn't call it an argument, but very long discussion about what it is, which at the end of the discussion, people will be like, I guess we need more observations to answer this. We still don't know. However, we have some sort of an ideas, and we have some experiments that we can perform. And first of all, I'm going to switch to something completely different, but bear with me. It actually connects with the black holes. This is the ultimate questions that I am sure that most of the sci-fi fans have at some point asked themselves. How powerful was a Death Star laser? All right. And we can do a very simple calculation. It's not difficult. We don't have to do anything fancy. We know that Alderon, when you look at Wikipedia, which everybody should look at Wikipedia, it's an amazing resource. We know that Alderon was roughly Earth size and Earth mass-like planet. And when you do the calculations of the binding energy, the necessary energy required to blow up an Earth-like planet, you will get that you read roughly 10 to the 32 joules. Now, if you go back to the film and you actually go through the sequence of trying to, when they blow up Alderaan, and you actually look at the laser, you realize that the laser pulse was roughly 4 seconds, which afterwards you get the exploding Alderaan, which I have to say for 1970s is an absolutely brilliant effect. And when you calculate, okay, in 10 to the 32 joules, the laser managed to deliver this energy in 4 seconds, you realize that the power output was 10 to the 31 watts, on order of 10 to the 31 watts, which is 140,000 solar luminosities. And by solar luminosities, I mean the entire energy output or energy power of a sun. So that is really nice laser, right? And now you might be like, okay, great, that star laser was really powerful, amazing technology. We don't have it. Why are you telling us about this? Well, because we can do the similar calculation for a galaxy and a supermassive black hole. I would like to point out that there are many different black holes, and you can see one example on the right, which is just brilliant. So energy output of a supermassive black hole, when it accretes, can be anywhere between 10 billion, or 10 to the 10, to 10 to the 14 solar masses. That's roughly billion times more powerful than a Death Star. Now you might be wondering, okay, can we do, what is the binding energy of a galaxy? Galaxies are massive compared to planets, and they are, and the binding energy is roughly 10 to the 52 joules. When you look at how much energy a black hole releases during its growth from this 500 solar mass seed that I was talking at the beginning, all the way to these, 100 million solar mass black hole, this beast, this hidden monster in the middle of the galaxy, it's 10 to the 44 joules. It's 100 times more than the binding energy of a galaxy. The supermassive black hole during its lifetime has the power to rip a galaxy apart. And we know that every single galaxy has a supermassive black hole in the middle. But we can see galaxies, right? When you look at Hubble, one of the famous Hubble Deep Fields, we see like thousands and thousands of galaxies. When you look at the all-sky surveys like SDSS or 2MASS, when you look at some of the images and very, very big catalogs, you see hundreds and millions of galaxies in the universe. So how is it that with all this power that supermassive black holes have, how is it that the galaxies survive? And if they survive, which obviously they survive, we live in a galaxy, can they actually change the galaxy in some ways? And this is where most of the disagreement comes to between the scientists. So first of all, that we look at it is that when you do what's something called a cosmological simulation, it's basically when astrophysicists who don't like to go to their telescopes and then decide that they want to do a simulation of the universe, a cosmological simulation, where they code all the necessary physics, they take some sort of, they look how the universe looked after the Big Bang, and then they started simulating this universe. They create a small box of the universe, not the whole universe, but the small box with loads and loads, like thousands and thousands of galaxies, and they can see how the galaxies evolve and everything. And they realized that they need supermassive black holes in their simulations in order to make sure that the universe they simulate looks like the universe we live in. And they need the supermassive black holes to basically inject energy, or basically release energy into their galaxies. And you can see this when I play the video ahead, is that the blue gas, that's the cold gas, and then you can see it at some point you create these red hot spots. That's basically the supermassive black holes heating the environment, the essential part. So can we actually see it as observers, right? I mean, astronomy is an observational science, right? We look at stuff, we are kind of famous for that with our telescopes and everything. And I would like to start with a very, very simple hypothesis. And that is, the more powerful a supermassive black hole is, or the AGN, the more energy it releases into its galaxy, right? Because it's more powerful, it can release more energy into it. And therefore, it can disrupt its galaxy, especially it can disrupt its ability to grow, which means its ability to shut down star formation, because that's how galaxies form, through star formation, through creating new stars. So you might actually say is that, okay, more powerful is going to be my supermassive black hole, the less star formation there should be, right? But when you look on the plot on the right, which is your star formation on the y-axis, on the vertical, and on the horizontal is the NGN power. By the way, this is just a sketch of a scientific plot. The data is, most of the things come from Flora Stanley's 2015 paper and from Chris Harrison's 2017 paper, but I just sketch it in Python to simplify the plot. And if you think it's kind of wonky for a computer graph, it's because I use the XKCD style of plotting things, which is such a shame we can't use in scientific papers because it's a brilliant way to plot graphs. Anyway, we see it's flat. It doesn't matter how powerful your supermassive black hole is, it's still kind of similar. There's still kind of similar star formation. That's the red points are the observations. When you kind of look at the results from the simulations, which is your blue curve, you actually realize that we agree. So even though supermassive black holes are vitally important in simulations, this first very simple experiment actually completely fails. And it probably fails because you measure your AGN, your supermassive black hole power, on scales of 1 million year, while you measure your star formation on scales to 10 to 100 million years. So basically, while something is oscillating very, very rapidly, the star formation is kind of lazy and it's hard to disrupt immediately, right? So it kind of destroys any correlation. Now, I would love to give you an answer and say, this is how supermassive black holes disrupt galaxies in their simulations. Unfortunately, this is kind of the edge of, there has been few papers after 2017, of course, but it's kind of, we are kind of stuck there. We don't really know that much more afterwards. So it's still one of the actually biggest open question in astronomy and galaxy evolution is what is the role of supermassive black holes? Okay, but assume that they are important, right? In simulations, they are really important. So what are the possible ways of actually doing this? Are there ways for the supermassive black holes to do it? And one of the ways to do this are radio jets. And radio jets give you the most spectacular images in the entire astronomy. I'm sorry, but they do. So each time in the middle on each of these images, you see galaxies in the middle, right? And then you see these jets going out of them in the opposite direction that suddenly kind of goes into these like kind of like bubbles, these blooms. We call them lobes in radio astronomy. First of all, what are jets? Jets are narrow streams of high energy particles that have a speed close to the speed of light, that are actually launched very close from the event horizon of the supermassive black hole, and they are basically these tiny lasers that shoot through that actually shoot out of the black hole, or very close from the black hole. And you can see that they can actually eject a massive amount of material out of the galaxy, and they really heat up their surrounding as well. So this is one of the ways to do it. Another way to do this is you can go have gas outflows. And now you might be wondering, wait, what is the difference between gas outflow and a jet, right? It kind of sounds the similar thing. It's just gas moving, right? There are actually quite massive differences. So outflows are launched are ejected. It's these gas outflows is this gas just moving at tremendous speeds of up to 3,000 kilometers, and they are sort of ejected. All this gas is ejected at the accretion because of the light pressure, photon pressure. You might be wondering, wait, light doesn't have pressure? Yes, it does. This is why solar sails are actually a vital thing for the next generation of satellites, that you can actually use the pressure of light from our sun to propel our satellites. Outflows can be massive. They can be as big as the whole galaxy, right? It can be this massive wind that just sweeps things in a galaxy. When you look at top right, you can see an image of, it's actually own data we published, and you can see the image that's your galaxy. It's how galaxy is bright. This is, by the way, how, when you look at very far away galaxies, that's how they look in even using the state-of-the-art telescopes. They just become blobs. We just look at blobs most of the time. And actually, you can kind of see where it's bright, you are forming the most amount of stars. And then you can see sort of the white contours, these huge white contours all around. That's actually indicating where an outflow is, right? And it's kind of this theory is that if outflow would be sort of disrupting star formation, then where you see an outflow, you wouldn't really see any of the light from the galaxy, right? Or you wouldn't see any light. You would see that image that's actually in the background, and that would be sort of very faint. But unfortunately, we don't see anything. One way you can look at the outflow, and unfortunately here I had to go to our friends in galactic astronomy rather than extragalactic astronomy, is that you can see on the bottom right, it's actually a supernova explosion. It's the bubble nebula. And there was a supernova in the middle. And can you see that bubble? It's actually a bubble. It's actually an explosion. It's a shockwave from an explosion from a supernova that's going, and it's sweeping all this gas. So if we would have an active supermassive black hole in our Milky Way, instead of this boring little thing that we do, that's called Sagittarius A star, and it's really boring, then we might see outflows like this. Unfortunately, we don't, because our galaxy is boring in every single way. So we don't actually see any evidence that outflows can have this rapid impact on galaxies either, which is kind of depressing. So conclusions. Every galaxy has a supermassive black hole in the middle. They are really common. They are nothing special. We have ideas where they originate, how they grow and everything, but unfortunately there are still many open questions of how they are actually born. We know how they grow, but we don't know how they are born. We know that supermassive black hole is so powerful when it starts absorbing and accreting gas that it can outshine an entire galaxy. For example, quasars are supermassive black holes accreting, and they are the brightest things in the entire universe. They have power to fundamentally change their host galaxy, but given how much power they have, it proves to be remarkably difficult to figure out how they are actually influencing their galaxy. So this is the end of my talk. Hope you enjoyed it. And if you have any questions, feel free to ask.
All right, so we've got a couple of questions. Ian, I think you might want to keep your talk up for a bit, but we shall see. Okay, so we have a question here from Dale Gusta, and that is, does the gravitational effect of an object dissipate until it reaches zero, as in if there's an actual horizon to the effect of gravity?
Oh, does he try? Is the question that, I assume that the question is there actually sort of zero gravitational potential energy at the event horizon? I hope I'm asking, I got the question right. Problem is we don't really know what is beyond the event horizon, so it's really hard to judge. We basically have absolutely no way of knowing. I think that's the answer to that question. It would be really cool to know, but once you would fall into the black hole, you can never come back and answer the question or tell the answer to everybody else. So kind of sucks, actually.
Yep, yet another unanswerable question. And then we have a couple here from Zuljin. Sorry if I'm mispronouncing that. And the first one is, why is the lower part of the black hole picture brighter than the top? The one of the, yeah.
Oh, that is an excellent question that I ask myself many times, but I never really figured out. It might be few things. The gas is probably rapidly rotating around it at like very high speed, close to the speed of light. So I wonder whether it's called, what is something called, it's actually boosting the energy. And that's actually why it's one part is brighter. It's called using special relativity. When you are very close to a speed of light, you can actually boost your emitting photons in a certain direction. So if the bottom bit is moving towards us and the upper bit is moving away from us, that might explain it. But unfortunately, I'm more of a galaxy evolution person than a supermassive black hole person. So it's just my theory. I'm not 100% sure.
Cool. Thank you. And then we have a second one here from the same person. How can you measure power over 1 million years or large distances, I'm assuming?
Okay, so this is one of the problems. You can't really measure the power for the past million or 10 million years. You might be wondering, like, how do we know that something changes on the scale of 1 million years and something else changes on the scales of 10 to 100 million years? So it's a tough, we know, given the size of the whole system, of the whole sort of the system, the supermassive black hole and the surrounding gas, that it would take, if you would suddenly bring a massive amount of gas, it would take roughly 1 million years for the gas to actually go through the entire system into the middle and brighten up the whole thing. So we know that these changes can't massively change on scales of 1 million years. That being said, there are a couple of supermassive black holes that have very strong, what we call variability, that can change on scales of 20, 30 years. But that is probably nothing like a fundamental change in their energy output. What's happening is that there is suddenly a little gas cloud that is somewhere close already. It quickly falls in, that increases the output for 10, 20 years, and then it kind of dies down again without any sort of, it's not a significant blip. We can measure them, but there's no significant. So yeah, but most of them, they don't change on scales of 1 million years because of their size.
Cool. And then I have another question here from Anders Kahl. That might have been a mispronunciation, apologies. And what is the current assumption on how the supermassive black hole formed that early in the universe, if you're allowed to guess?
So we know that roughly 200 million years after the Big Bang, when the first galaxies appear, the universe was very much different to right now. For one very simple reason: there were not many metals. Now, by metals, I mean astronomy definition of metals, which is any element heavier than helium. That's how astronomers define metals. Chemists, please don't kill me. I know it's weird. But metals or anything heavier, they actually would very much help you with cooling. So there must have been enormous amount of hydrogen gas. And this hydrogen gas was allowed to create massive star clusters, which would explain this loads and loads of supermassive black holes that could then merge, or would actually explain why you could do some like a massive cloud collapse directly into a big black hole. I can't tell you which one is currently preferred, because both of the solutions to these problems have problems, and both of them have perks at the same time. There has been some evidence around 5 years ago that maybe we have observed one of these seed black holes in using HST, Hubble Space Telescope. But it we just don't know anything about our young universe to really pinpoint one way or the other.
All right, sounds good. And I have one more question. I think this is a pretty good wrap up one. And that was, What would help to kind of help to answer some of the open questions in supermassive black hole formation? Would that be more observations, better telescopes, or different observations from different instruments? Kind of what would you like to see to be able to understand these objects better?
So when it comes to the seeds, to the black hole seeds, how they create, two of it. Bigger telescopes are always better. You collect more light, you see a better resolution. So that's JWST, that's hopefully going to be launched soon, can actually answer that, because it was tuned to very young universe, to observe young universe. The European Extremely Large Telescope, which is going to be a 38-meter mirror, which is awesome. That's going to be available in about 10 years, maybe 15. This might be big enough. I would really like to see results from ELISA, which is this future telescope, but designed not for light, but for gravitational waves. Because if we can catch gravitational waves from merging of these seed black hole masses all the way from the earlier universe, from the young universe, we might be able to, it's a completely different look at the problem using completely new set of tools, and it might just show you how often these black holes merged and what were their masses, how big they were when they were merging. So that might be a very good idea. Just, go non-standard astronomy.
Perfect. Sounds good. Okay, thank you so much, Jan, for your talk. And now we are going to take a quick 5-minute break, and in about 5 minutes, we're going to be back hearing from Kirsten. Alrighty, and we are back. So if Kirsten wants to share your screen, you can take it away.
I hope you see my screen.
Yes, we do.
Can you see my slides?
Yes, I can.
Excellent. Good. So I'm going to go away from the really heavy beasts that Jan was talking about with the very massive black holes and just look at what they're sitting in, the galaxies. I'm going to go to sort of the dawn of time. It's not quite true because we're going to be just a little bit after that, but we're going to go look for the earliest galaxies. And it's not changing on my slide. Is this not working?
It's not changing for me.
No, it's not changing for me either.
Mine is being funky though. Maybe you want to unshare and then share again.
That's something happened. Huh. It looks like I'm just gonna have to get, and now changed. Does it work?
Yep, I can see
Good.
it.
Okay, this is a view of the sky seen from the southern hemisphere, actually from one of the big European observatory, southern observatory places. We're actually seeing the night sky and actually seeing the beautiful band of the Milky Way across the sky. And this is actually what you see here is this sort of, well, here it just looked like a kind of a reverse U-shaped thing, but it is fact is a big disk. And so our home is on planet Earth, which is orbiting around the sun and the solar system is a part of the Milky Way. The Milky Way is our home galaxy, and the Milky Way has about hundreds of billions of stars, and it's about 100,000 light years across. So it's a relatively big thing, a big home to live in. Again, most of the stars we see on the sky are actually from stars in the Milky Way, and we have very, very few, just sort of looking by eyes, very few other galaxies we can see. We can see some of the nearest neighbors, but that's about it. And of course, this has affected our worldview for many, many, many years, for many centuries and decades and millennia and so on. And from a point of view on Earth, for a very long time, there was the perception that we were in the middle of the world. Maybe this is not a big surprise if you're limited to actually just your observations with what you see with your eyes. So there's been various, maps or suggestion models for what should be the world, what the world looked like, but they've typically been the geocentric ones with the Earth in the middle and everything orbiting around it. Now, as we got telescopes and got better measurement facilities, it actually shifted into the heliocentric worldview where the sun was in the middle and the Earth, together with the other planets, were orbiting the sun. Now, the heliocentric worldview actually persisted for quite a while and even in different flavors. And trying to map out the Milky Way, seen in the sky, seeing this big band, was one of the ones who set out to do this was William Herschel, who mapped out as basically as a big disk, the disk of the Milky Way, but it was still basically placing the sun towards the center of this disk structure, so the Milky Way. So sort of maintaining a bit some of this heliocentric worldview. My microphone is making a little noise. Uh-oh. Does it help if is that? No, that didn't help either. Is it okay? Okay, good, I'll continue. So moving on, about 100 years ago, there was a change in our worldview, and one of the ones who was really contributing to this was Shapley, who was measuring where the globular clusters that were seen away from the Milky Way disk, Milky Way plane, were seen to be in distributed across different, like not around where the sun is, but in a location further away from the sun. So they were sort of centered around something else, and that certainly put the sun in a much further away position, not in a central location of the Milky Way. And so we moved into what was a more galactocentric worldview. However, actually realizing that the sun. So yeah, with this realizing that the sun is about 25,000 light years away from the center. But around the same time, there was actually a lot of effort understanding what all these nebulas that we're seeing on the sky actually were. And at some point dawned the realization that these are actually galaxies outside of our Milky Way. And so the Milky Way is just one galaxy among many other galaxies. And that investigating the distribution of the other galaxies and understanding that the universe is actually an expanding universe led to the fact that we understand that we don't have a specific center of the universe. It is an acentric universe. And so moving on from that, we use galaxies. Galaxies are really important both for understanding where we are, because the Milky Way is our home. So the evolution, how do galaxies actually form and how do they evolve to what they are today? But they're also essential for actually understanding cosmology and the structure of the universe. And through very intense efforts, we now have a fairly established picture of what is the history of the universe, starting here on the left-hand side with the Big Bang and ending up today, measuring in age about 13.8 billion years, which is a fairly long time for our time scale, but it's a decent time for galaxies to evolve. Now, if we take after the Big Bang, came the time when hydrogen was formed, and that was formed through the combination of protons and electrons combining into actually becoming hydrogen atoms, and together with this also the helium. And this is essentially everything that we got out of the Big Bang. This was our periodic table at that moment. In this process, we got what was known today as the cosmic microwave background radiation, which is the light and the energy that was released in the recombination. And this is effectively the first light we have in the universe. But then this followed the dark ages, as we call them, up until the first stars and the first galaxies actually started forming. And there are different models that say this could be 100 million years after the Big Bang, could be 200 million, 300 million years after the Big Bang. But it is somewhere around 200 million years after the Big Bang. And then came trying to actually find these very first objects is really important because it helps us understand the origin of galaxies. But we're not quite there yet. We're not pushing into finding the very first objects. We're just about maybe 400 or 500 million years after the Big Bang. And I'll show you some of these examples afterwards. After that, it's just about waiting for another 13 billion years, and you have the galaxies as we see them today. And that is, of course, also a really exciting epoch, waiting for those 13 billion years. But the very first parts is actually looking at the early childhood of galaxies. If we look at galaxies today, we have particularly two main classes of galaxies. There are the elliptical galaxies, which is an example on the left side. And then there are spiral galaxies, which is an example on the right side. So the elliptical galaxies, the one on the left side, looks rather structureless and somewhat boring. And they're in fact not very boring. They just have a lot of very old stars, but nothing new is happening in the meantime. On the other side, the right side, the spiral galaxy has a lot of structure. They're very beautiful. And they have the blue stars that are seen in the spiral arms because there's a lot of young stars. There's still a lot of star formation going on. And again, remembering here now that galaxies with a lot of young stars, they tend to look blue. This is important. Now, if we look at galaxies in the early universe, this is one of the very deep fields done by the Hubble Space Telescope, where it's been staring for, I think, about 10 days or something like this on the same piece of sky and just looking deeper, deeper, deeper and collecting more and more photons to actually see really far. And this image, which is one of the ultra deep field or the extreme deep field, has about 5,000 galaxies. It was very difficult to see because the screen resolution doesn't really allow to see this, but in fact, there is a lot of galaxies. And these are looking back about 13 billion years. So it is quite impressive. But now when we look back so far in time, we're looking at cosmological distances. And because the universe is expanding, this has an effect on how we see the light. So if you look on the upper left-hand side, you have the upper right-hand side, you have the Big Bang starting, and then you have a smaller universe and gradually expanding. And of course, this is the space that is, so it is the space between the galaxies that is expanding. It's not the galaxies themselves not expanding because of this, their gravitational bond, but the space is expanding. So light that's emitted as blue will gradually be shifted. It's effectively the same as a Doppler shift. It will be we will observe it as longer and longer wavelengths. So something that was emitted as being blue will actually look more like a red thing later. And it's because of the expansion of the universe. And this shifting from the blue towards the red is what we call redshift. So you often hear astronomers, galaxy people talk about, like, what is the redshift of the galaxy? And then you can translate this into a distance to the galaxy or how old the universe is at that time. This is just to show again that in fact, ultraviolet light, which we see on the right side, can be shifted so much that it actually ends up in the infrared part and actually goes through the visible light, which is what we see with our own eyes. And this, of course, affects how we are actually able to find early galaxies. So this is just a little cartoon that I tried to make. We have a little observer who is actually looking at a bluish kind of galaxy. Now, if the same galaxy was at a much bigger distance, like some cosmological distance, the light will have been shifted from this bluish to this more greenish yellowish part of the spectrum. If the same one is actually even further away, the same galaxy is seen, it's even more red. And that means that even if we're looking for blue galaxies with blue light because they're young stars, we actually have to look in the red part of the spectrum. And what are we using? We're using all kinds of telescopes. I'm an observer and I need telescopes, and so do all my colleagues. We need good telescopes, big telescopes, and we need telescopes that have good quality, can give good imaging quality as well. So here's a little sample or a little bit of examples of different types of telescopes that we're using. The three ones on top are space telescopes, where Hubble is more primarily optical and infrared. Spitzer is really infrared, and Herschel is the longer part of the infrared. So really seeing the emission that comes from the dust and the gas, while Hubble would more be seeing the light from the stars. Now, all the five other ones that are below, we have the ALMA telescope, which is one of my favorite telescopes, and also was the one that Carmen talked about last week, or at the past, like a month ago. This is the absolute most sensitive telescope we have at millimeter wavelength, and there we're also looking at the gas and the dust. And this is actually, the gas and the dust is extremely important because this is the fuel, this is the stuff that makes the stars. The same also looking, the one below, that's called the Very Large Array. It's a big radio array in the US. And then we have on the right-hand side, it's the Subaru, the CAG, and the VLT, the Very Large Telescope, which are all optical telescopes that also can do a little part of the near infrared, but they're located in different parts of the world. And again, these are all big international facilities. And it's really important to have big international collaborations in this. You should also notice astronomers are not always very imaginative with their telescope names, like the Very Large Telescope. So now I'm going to shift away from what the kind of telescopes we're using. And before I'm going to show examples of galaxies we're actually seeing, I'm going to first show you what we might think that they could be from simulations. Because there's a lot of effort going into actually making models of what galaxies might look like. And this is an example from a simulation where you have about a merger, or this, like the same galaxy can look different at different times. So the top one, like let's see, the left column is seen from the top, and it's on the right column is actually the same galaxy in the simulation seen from the side. So one is top view, one is side view. And you can see that it looks a little bit sort of mixed up, and there's a little bit of stuff floating around and so on. And again, it's a simulation. This is not exactly how we see the galaxy. If we wished, we could get this much detail. But, and this is seen about 800 million years after the Big Bang. But you can see that it looks like there are two galaxies that are actually colliding with each other, and slightly bigger and a slightly smaller one. It's what we call a merger, because they will merge and become one galaxy. Now, the same galaxy you can see in the lower panels, which is actually seen as a regular spiral galaxy. And so if we're now looking for, should I expect that I find spiral galaxies, or do I expect to find merging galaxies, or maybe both? It gets even more complicated, because the same galaxy seen a little bit later in the same simulation looks like a disturbed disk, where the disk has been affected by some small stuff that came onto it and then becomes a little wobbly as well. So the same galaxy can look very different at different times in its life. But that was just a zoom in on just one specific galaxy. This is from a different simulation. In fact, it's a movie that's several minutes long, so I just took a few screenshots instead so you can see it. It's a much bigger volume. You can see many different little galaxy parts or galaxy bits. And as we step through from high redshift, from early universe, gradually, and you can see they shifted a bit. Some of them grew and became a bit bigger. We wait a bit longer, you can see they're growing even bigger. Some of them are getting very close to each other. You can see they're changing a bit in color. They're becoming more red because they have more old stars now. And now it's all merging into something that looks like one sort of bigger galaxy, and eventually becomes a really big galaxy. So I think you here can see how going from this little galaxy clumps eventually becomes this bigger galaxies we see today. So we're not actually looking for like one specific early galaxy. We're looking for all these like things that are the building blocks of what we get today. Now, what do they look like when we're actually looking at this in the sky? I'm going to show you a few different examples just to illustrate how tiny these little things are in the sky. Why it's so difficult to actually get any kind of detail. I'm going to use a couple of examples that I have actually looked at, and also examples from other scientists throughout the world. So this is actually a galaxy cluster. So don't look at the big galaxies in the front. They're just effectively just a lot of mass, and they act like a gravitational lens. So they make the light from the galaxies behind even brighter. You won't see actually very easily which one we're going to be looking at, but there's this tiny little thing in there. And I put a tiny little error bar, not an error bar, just a bar in it on the side, this little white line, to show this is about the size corresponding to about 5,000 light years. So remember, the Milky Way is about 100,000 light years across. So something this small might actually grow into be something like our Milky Way. We don't know if this one will, but galaxies that size could. Also, if we actually weigh the mass, basically figure out how much stars are in there, we'll see that it's a few billion times the solar mass. So it's about 1/10 of what, 1/20th, about 5% of what our Milky Way has today. So it takes quite a while before this galaxy would actually grow into the size of the galaxies we see today. It's more like what we call as a dwarf galaxy. This one is about 1 billion years after the Big Bang. So it's not really like one of the very first kind of galaxies, but it is very much looking like what we expect them to be. Here I show another image of it as well, which is actually carbon. We're looking at atomic carbon. And what we're really trying to find is not just the light from the stars, we're really trying to find the gas as well. And if it looks bigger here, all the contours, the little lines, it's just because the resolution, we didn't get as good a resolution to actually see something. So it looks more blurry than it actually is. Now here's another one, which is, it has a story to it. We had observations with ALMA of this area, but weren't looking specifically for this galaxy. And then a colleague from Copenhagen called me up and said, I see you have data on this. Can you look at this little place up there? And this is actually about where this little the white box is. And said, do you see anything? I said, wow, we maybe see a little bit. It's like, well, look harder. Like, and in fact, actually, this was the first galaxy where we were really at such a big distance, we were finding a massive amount of dust. But I'll show you first how difficult it actually is to see it. So that little white box is that tiny little red smudge that we're looking at. And again, this is behind the galaxy cluster, so the light is amplified. We see it much stronger than it is in reality. And turns out that this actually has a multiple little components together that might actually be merging with each other. And so it shows sort of the complexity of this. Here's another example. This is with my with colleagues from Japan, where this is a somewhat slightly similar kind of galaxy. Also, there's about 700 million years after the Big Bang. And the galaxy is about 15,000 light years across. So it's a bit bigger than the one we saw, the first one I showed. But in fact, it actually looks like it's two kind of galaxies that are merging. And then it has both, which is dust. Again, it's like the little dust particles we see. We see oxygen, we see carbon. And because of that, my Japanese collaborator said, oh, we have three things in one go. So it's like the three big dragons. And this is the artist impression that they did with the press release. And just imagine if galaxies look like this. That'd be fantastic. But we don't see those kind of details. Another one, this is actually going into about 600 million years before the Big Bang. And this is one of the most distant ones we know of. They all have funny names, just letter and number combinations. This one is called EGSY 8.7. And that's because of the redshift. This one is in the northern hemisphere, so we can't use ALMA observations. We can't use the Chile telescopes for this, which is a bit of a shame because I think there would be a lot to be learned here. And I take the record holder as my last one that I'm going to show here. And this one is less than 400. No, this is not the record holder, sorry. This one is another one. What you're seeing here is, again, you can see how extremely tiny these things are. The light that's actually being blown up here and showing this sort of blurry structure is actually looking at the oxygen. And now we get to the record holder, which is at redshift 11, for those who actually appreciate the distances or actually can relate to numbers. In more human numbers, this is actually universe age, about 400 million years after the Big Bang. It is extremely tiny. It's about 4,000 light years big. It's about a billion times the mass of the sun. So it's a tiny little object. And this is probably one of the biggest ones of those that exist at that point, which is why it's actually possible to actually get the distance right. So there are many more examples of this in the available, but I try to take sort of this, showing how difficult it is to find these tiny little things that are eventually going to become these really big, massive galaxies. So if I just put it back onto our history of the universe and take these tiny little structures, these little building blocks, it's like getting a Lego box where you want to build everything together and eventually one day you get a big galaxy. So about 13 billion years later, we have things that looks like the Milky Way. So I'm just going to start there. So stop there with the perspective of home and really far away galaxies, and I'm happy to take questions.
Thank you so much, Kirsten, for your talk. So the first question we have is from Zuljin, and that is, why can't we see the first stars in galaxies? And if we can't see them, then how do we know that they exist in the first place?
So one of the reasons why, well, we maybe can actually see them, but we don't know yet. And one of the reasons we don't actually know what we're looking for, there's a lot of different models and simulations that suggest what they could look like. Some say that maybe it's like single stars, others think that there are whole clusters of stars, others think that it is maybe almost a full little dwarf galaxy or something like this. They're also very, very short-lived because they're basically like this gigantic thing that will collapse and then go away in some kind of big explosion, basically. So they're really far away. They might not have enough light that we can properly see them unless we have a really, really, really big telescope. So we don't know yet exactly what we're looking for and what we might be seeing.
Perfect, thank you. And a second question here is from Chester Elmroth, and that is, can some of the cosmological redshift be attributed to scattering and not just the Doppler effect?
Scattering in what way, I would think, is, I think when we're out in these very big redshifts, then it is really the cosmological, the expansion of the universe that's pulling this. If you're looking at things that are more close by, we will have more local motion as well. So if you have, for example, a cluster of galaxies that are together, they will move relative to each other as well. And so they will not fully represent only the full distance to where they are. They will also give a little bit of, they will have some internal motion, the motion relative to each other. But that's really, you see particularly galaxy clusters as well.
All right, thank you. And we have another question from Andrew's call. He says, great presentation. The early galaxies are very bright in oxygen, parentheses, question mark. And does that indicate early star formation, or sorry, early supernova activity as well?
Yes, so there's a lot of discussion going on why we see so much oxygen. And this could indeed have something to do with what are the kind of, the evolution of the early evolution of the young stars. But it is not necessarily a given thing that we're seeing a lot more oxygen than we expect. It could also be that we have a harder time seeing the carbon because some of the carbon could be locked either in molecules or they could be ionized so much that we don't actually get them into transitions that we easily see. So, but yes, there seems to be in the very early galaxies, there seems to be that they have a high oxygen ratio.
All right, I am not seeing any more questions here. I guess I'm just going to ask you the same question that I asked Ian at the end, because I thought it was quite a nice summary question. And that is, what is, for you personally, what would you like to see? Oh, hold on. I'll finish that in just a second. There is one more. And it is from George Gao. And that says, can we, oh, sorry, hold on, translating this for a second. It says, can we get some better ground truth for some of the simulations you shared? He says, for example, can we ever look at the same galaxy through multiple snapshots in time? Oh, sorry. How can we better ground truth to some of the simulations? Does that make sense?
Oh, so one is how can we better constrain the simulations?
Yeah.
And there, yes, we can do that as we're getting better understanding of the data we're getting in. Because then we can probably rule out some of the models we're seeing or that have been produced. There's been quite some, but it's also, we need to understand, what we discovered is that galaxies in the early universe don't quite look like what we expected them to be. So there's been a lot of going like, oh, they should all be looking like this. And then people observe them and say, oh no, they're actually looking like this other way. And it's like, oh, maybe our expectations were not quite right. And so it's a slow process where we're understanding that things didn't quite look the way we expected it, but maybe we missed something, and then they build on top of each other. But there was another question that, I don't know if this was actually in that question or not, whether that was you, Kiana, interpreting the question. But there's also for the can we observe the same galaxy long, like, or basically how can we see the evolution of a galaxy over a long time, and we can't because we live simply too short for this. We need a few 100 million years to basically see this. But what we can do is that we try our best to connect with the different types of galaxies we see throughout the different times of the universe. So it's a bit like looking at children in the Middle Ages and then try to understand what adults look like today, sort of extrapolating between or interpolating between something really early in our history to what we're actually seeing of older people today. So.
Yeah, that's a good way of putting it. And then, okay, I think that's all of the questions from the live chat. So then I'm going to ask the question again of what would you personally, if you could have, okay, I have this telescope tomorrow and I have observing time on the telescope as well. What would you like to see for the development in your field?
I would love to be able to look for really like the gas, like the where the gas is actually turning into stars. But that means that we will have a hard time actually finding the very first ones, but we just really want to push in really, really early to some of the very almost first ones, because then we're basically finding the cradle of the star formation, like where the newborn stars are. And I think if we can find these tiny little building blocks, then we can actually get a really good handle on what the models are doing as well. So yes, I want to look at the gas and the dust.
Good answer. All right, thank you so much for your talk. And if people had more questions and didn't get a chance to put them into the live chat, you can always message us on, or email us, or message us on Facebook or Twitter, or any kind of format for asking. We are here to answer your questions. And again, we are going to take a short break and we'll be back with the quiz in just a couple of minutes. All right, and we're going to have Holly take over for the quiz now. You are muted, Holly.
Hi everybody. So you should now all have the quiz form on the screen on YouTube, and we'll be sharing, rather than doing Kahoot, we'll be sharing a link to this in the chat for you all to go on and fill out a Google form. So this is not going to have as much of a time limit as we usually do with the Kahoot quizzes, but there still will be probably about the next 5 minutes for you to fill out this quiz. And then at the end of it, we'll be able to figure out by checking all your responses who the winners are. So just as a general reminder, please do abide by fair play during this. Don't Google all the answers. It's less fun for you. So, just give it your best guess. And there are 2 required questions that you have to answer. So one of these is your team name, and the other one is you do have to tell us if you have any astronomers on your team, because we do expect that some of those might find some of these questions easier. But I'll just read through the rest of the questions now, and in your own time, or you can answer the questions as I read them through. There are 2 rounds to them. So one round has 10 general astrophysics questions for you that are all multiple choice. And then after that, we also have a second round, which has 5 questions, which are a bit of a music round. So hopefully you'll be able to hear those through my screen, but if not, you could click on the music yourself when you go and fill out the form. So question 1, how massive is the supermassive black hole at the center of our galaxy? Is it A, 4 million solar masses, B, 65 million solar masses, C, 19 million solar masses, or D, 7 billion solar masses? So that's for the supermassive black hole at the center of our galaxy. Question 2. How far back in time can we see by looking at the cosmic microwave background radiation, or the CMBR? So is it answer A, 8.6 million years? Answer B, 300,000 years? Answer C, 10.3 billion years? Or answer D, 13.8 billion years? And again, that question was, how far back in time can we see when looking at the cosmic microwave background radiation? Question 3 is, what type of galaxy is most common in the universe? And this is one of 3 options. So is it A, irregular galaxies, B, elliptical galaxies, or C, spiral galaxies? The next question is, how do astronomers detect that galaxies are moving away from us? Is this A, the shift in the spectral lines of the galaxies, B, the steady dimming of the galaxy's light, or C, the disappearance of the most distant galaxies? Next question is, what is meant by the term redshift? Is it A, galaxies appear redder if they are farther away? Is it B, the galaxies are becoming cooler? Or is it C, the spectral lines of the galaxies are shifted to redder wavelengths? Next question, what is the name of the closest large spiral galaxy to our own Milky Way? Now, is this one A, Andromeda, B, the Large Magellanic Cloud, C, M33, or D, NGC 2143? Next question is, what is the C in Einstein's famous equation, E equals mc squared? So what does it stand for? Is it A, the age of the universe, B, redshift, C, speed of light in a vacuum, or D, the Doppler effect? So our next question is, what is a supernova? Is a supernova the explosion of A, supermassive black hole, B, massive star, C, white dwarf, or D, neutron star? The next question, so second last question for the general question round, is which of the following ideas make up the Big Bang Theory? And this question is actually slightly different to the other ones because you can choose more than one option. So it might be more than one option to be the correct answer here. So which of these are correct? Is it A, the universe is currently expanding, B, the universe was once hot and dense, C, the universe has a finite size, or D, the universe is infinite? And the final question of the general question round is, the cosmological principle is the idea that the universe is blank. So is it that it is homogeneous, or is it that it is isotropic? Is it C, that it has the same physical laws throughout, or is it D, that it looks pretty much the same everywhere on large enough scales? So that was a pretty quick run through of the 10 questions we have in our general question round. And I just want to show you the next round that we have. So we also have an additional music round for this week's Astronomy on Tap quiz. So you should all be able to connect to the links in a Google Drive, which will have 5 different samples of songs. And all of these songs have astronomy or space themed words in their title, but we've only given you the first 10 seconds of the song. So hopefully you can guess it. I am going to have a go at trying to play those for you on YouTube as well. So if it doesn't work, let us know in the chat and I can try and figure out how to make it work. But here is question 1. So which song is this? So I'll play that a second time for you and then go back to the possible answers. Now, I've been told that we cannot hear it, so I will just check if there is a way I can. 1 second. Okay, there is not a quick way in which I can change my screen sharing so you guys can also hear it. So unfortunately, you'll have to play the music yourselves on your own screens. But hopefully if we do this again next week, we will fix it for you. But the first question, which hopefully you all have had a chance to listen to that sample, there are 4 different options. So one is it Counting Stars by One Republic? Is it Supermassive Black Hole by Muse? Is it Stars by Skillet, or Galaxies by Laura Veers? So there's also the sample from question 2. So with that one, Dancing in the Moonlight by Top Loader, Life on Mars by David Bowie, Starlight by Muse, or Black Star by Radiohead? We've also got question 3. So is that one Champagne Supernova by Oasis, A Sky Full of Stars by Coldplay, Total Eclipse of the Heart by Bonnie Tyler, or I Took a Trip on a Gemini Spaceship by David Bowie? Question 4, is that one All of the Stars by Ed Sheeran, Drops of Jupiter by Train, Fly Me to the Moon by Frank Sinatra, or Rocket Man by Elton John? And the final question, is that one NASA by Ariana Grande, Looking for Astronauts by The National, City of Stars by La La Land, or The Galaxy Song by Monty Python? So again, I hope you all had fun with the music round. Unfortunately, due to technical difficulties on my end, I didn't manage to get those songs for you, but hopefully you've all had a chance to listen through to the samples yourself. And we'll give you another couple of minutes to listen to those and answer the questions, and then get back to you with who has won the quiz. Okay, that's enough time, I think, for everybody. So we're just going to quickly check the responses and let you know who the winner was. Okay, so we can confirm that we have checked the answers, and the winner is Huzzah, with 14 questions correct out of 15. So well done.
All right, I can take back over for you, Holly, unless, is there anything else for the quiz?
Nope, that's everything. Thanks.
So thank you so much for the quiz. And just the last thing we have to talk about here is our next Astronomy on Tap. So tentatively, we have that set for the 23rd of June, but things might change, all the coronavirus madness, so not 100% sure how this is all going to pan out. And so hopefully just, keep an eye on Twitter, on Facebook. If you want to, you can always shoot us an email just confirming when we're going to be having the next one, but we should be posting those events once we have them set up. And we believe that the speakers for that are going to be Juliana and Paul. And yeah, so just stay tuned. Again, shoot us any kind of questions that you might have had left over that we didn't get to answer, or anything else that was on your mind. So thank you so much.